Convolutions and the fast Fourier transform. As a final topic in this chapter, we show how our basic recurrence from 5.1 is used in the design of the fast Fourier transform, an algorithm with a wider range of applications. The problem, given two vectors a equals to a0, a1, a2, and so on until an minus 1, and b equals to b0, b1, b2, and so on until bn minus 1, there are a number of common ways of combining them. For example, one can compute the sum producing the vector a plus b equals to a0 plus b0, a1 plus b1, a2 plus b2, and so on until an minus 1 plus bn minus 1. Or one can compute the inner product producing the real number a dot b equals to a0 b0 plus a1 b1 plus a2 b2 and so on plus an minus 1 bn minus 1. For reasons that will emerge shortly, it is useful to write vectors in this section with coordinates that are indexes starting from 0 rather than 1. A means of combining vectors that is very important in applications, even if it doesn't always show up in introductory linear algebra courses, is the convolution a star b. The convolution of two vectors of length n, as a and b are, is a vector with 2n minus 1 coordinates, where coordinate k is equals to the summations of ai times bj, summing for all those pair ij such that I plus j is equals to k, and I is less than n and j is less than n. In other words, a star b, a convolution b is equals to a0 b0, a0 b1 plus a1 b0, a0 b2 plus a1 b1 plus a2 b0, and so on until the last term, which is an minus 2 bn minus 1 plus an minus 1 bn minus 2 and an minus 1 times bn minus 1. These are the last two terms. This definition is a bit hard to absorb when you first see it. Another way to think about the convolution is to picture an n by n table whose ij entry is ai bj like this. a0 b0, a0 b1, and so on. And the last two terms of the first row is a0 bn minus 2, and the last term of the first row is a0 bn minus 1. For the second row, the first term is a1 b0, the second term is a1 b1, and so on until the last term. Last to next term is a1 bn minus 2, and the last term of the row 2 is a1 bn minus 1, and so on. And then to compute the coordinates in the convolution vector by summing along the diagonals. It's worth mentioning that unlike the vector sum and the inner product, the convolution can be easily generalized to vectors of different lengths. That is, a equals to a0, a1, a2, and so on until an minus 1, and b equals to b0, b1, b2 until bn minus 1. In this more general case, we define a convolutionalized b to be a vector with n plus n minus 1 coordinates, where coordinate k is equals to the summations of ai times bj, summing for all ij pairs such that I plus j is equals to k and I is less than m and j is less than n. We can picture this using the table of products ai bj as before. The table is now rectangular, but we still compute coordinates by summing along the diagonals. From here on, we'll drop explicit mention of the condition. That is, I is less than m and j is less than n in the summations for convolutions, since it will be clear from the context that we only compute the sum over terms that are defined. It's not just the definition of a convolution that is a bit hard to absorb at first. The motivation for the definition can also initially be a bit elusive. What are the circumstances where you'd want to compute the convolution of two vectors? In fact, the convolution comes up in a surprisingly wild variety of different contexts. To illustrate, we mention the following examples here. A first example which also proves that the convolution is something that we all saw implicitly in high school is polynomial multiplication. Any polynomial a of x equals to a0 plus a1x plus a2x squared and so on plus an minus 1x to the n minus 1 can be represented just as naturally using its vector of coefficients a equals to a0, a1, a2, and so on until an minus 1. Now, given two polynomials a of x equals to a0 plus a1x plus a2x2 plus a3x to the cube and so on plus an minus 1x to the n minus 1, and b of x equals to b0 plus b1x plus b2x squared and so on until plus bn minus 1x to the n minus 1, consider the polynomial c of x equals to ax times b of x that is equal to their product. In this polynomial, c of x, the coefficient on the x to the k term, is equals to ck equals to the summations of ai times bj, summing for all pair ij such that I plus j is equals to k. In other words, the coefficient vector c of x is the convolution of the coefficient vectors of a of x and b of x. Arguably, the most important application of convolutions in practice is for signal processing. This is a topic that could fill an entire course. So we will just give a simple example here to suggest one way in which the convolution arises. Suppose we have a vector a equals to a0, a1, a2, and so on to an minus 1, which represents a sequence of measurements such as a temperature, or a stock price, sampled at n consecutive points. Sequences like this are often very noisy like due to measurement error or random fluctuations. And still a common operation is to, by averaging the measurements, each value ai with a weighted sum of its neighbors within k steps to the left and right in the sequence. To the weights decaying quickly as one moves away from AI. For example, in Gaussian smoothing, one replaces AI with, for example, in Gaussian smoothing, to the prime equals to 1 over 0 AI times the summation of aj times e to the AI prime equals to minus over j minus I to the square, the summation of all j starting from I minus k times e to the next minus to I plus k, j minus I to the square, where the index j is starting from I minus k to j equals to I plus k. So for some width parameter k, and with z chosen simply to normalize the weights in the average to add up to 1. There are some issues with boundary conditions. What do we do when I minus k is less than 0 or I plus k is greater than n? But we could deal with these, for example, by discarding the first and the last k entries from the smooth signal, or by scaling them differently to make up for the missing terms. To see the connection with the convolution operation, we picture this smoothing operation as follows. We first define a mask, which is w equals to the vector w minus k, w minus k minus 1, w minus of k minus 2, and so on until w minus 1, w0, w1, and so on until wk minus 1, wk, consisting of the weights we want to use for averaging each point with its neighbors. For example, w equals to 1 over z times the vector e to the minus k squared, e to the minus k minus 1 squared, e to the minus of k minus 2 squared, and so on until e to the minus 1, 1, e to the minus 1, and so on until e to the minus k minus 1 squared, e to the minus k squared. In the Gaussian case above, we then iteratively position this mask so it is centered at each possible point in the sequence A, and for each positioning, we compute the weighted average. In other words, we replace AI with AI prime equals to the summations of ws times ai plus s, summing for all s starting from equals to minus k to s equals to k. The last expression is essentially a convolution. We just have to warp the notation a bit so that this becomes clear. Let's define b equals to b0, b1, b2, and so on until b2k by setting bl equals to wk minus l. Then it's not hard to check that with this definition. We have the smoothed value ai prime equals to the summations of aj times bl, summing for all pair jl such that j plus l equals to I plus k. In other words, the smoothed sequence is just the convolution of the original signal and the reverse of the mask, with some meaningless coordinates at the beginning and end. We mentioned one final application, the problem of combining histograms. Suppose we are studying a population of people and we have the following two histograms. One shows the annual income of old men in the population, and one shows the annual income of old women. We'd now like to produce a new histogram showing for each k the number of pairs MW for which man M and woman W have a combined income of k. This is precisely a convolution. We can write the first histogram as a vector a equals to a0, a1, and so on until am minus 1 to indicate that there are ai men with annual income equal to I. We can similarly write the second histogram as a vector bq equals to b0, b1, b2, and so on until bm minus 1. Now, let ck denote the number of pairs m, w with a combined income k. This is the number of ways of choosing a man with income ai and a woman with income bj for any pair ij where I plus j is equals to k. In other words, ck is equals to the summations of ai times bj, summing for all pair ij such that I plus j is equals to k. So the combined histogram C is equals to serial C1, C2, C3, and so on until Cm plus m minus 2 is simply the convolution of A and B. Using terminology from probability that we will develop in Chapter 13, one can view this example as showing how convolution is the underlying means for computing the distribution of the sum of two independent random variables. Computing the convolution. Having now motivated the notion of convolution, let's discuss the problem of computing it efficiently. For simplicity, we will consider the case of equal length vectors, i.e. m equals to n, although everything we say carries over directly to the case of vectors of unequal lengths. Computing the convolution is a more subtle question than it may first appear. The definition of convolution, after all, gives us a perfectly valid way to compute it. For each k, we just calculate the sum, the summations of ai times bj, summing for all pair ij such that I plus j equals to k, and use this as the value of the kth coordinate. The trouble is that this direct way of computing the convolution involves calculating the product ai bj for every pair ij in the process of distributing over the sums in the different terms, and this is theta of n squared arithmetic operations. Spending big O of n squared time on computing the convolution seems natural, as the definition involves big O of n squared multiplications ai times bj. However, it's not inherently clear that we have to spend quadratic time to compute a convolution, since the input and output both have size big O of n. Could one design an algorithm that bypasses the quadratic size definition of convolution and computes it in some smarter way? In fact, quite surprisingly, this is possible. We now described a method that computes the convolution of two vectors using only big O of n log n arithmetic operations. The crux of this method is a powerful technique known as the fast Fourier transform, FFT. The FFT has a wide range of further applications in analyzing sequences of numerical values. Computing convolutions quickly, which we focus on here, is just one of these applications. Designing and analyzing the algorithm. To break through the quadratic time barrier for convolutions, we are going to exploit the connection between the convolution and the multiplication of two polynomials, as illustrated in the first example discussed previously. But rather than use convolution as a primitive in polynomial multiplication, we are going to exploit this connection in the opposite direction. Suppose we are given the vectors a equals to a0, a1, a2, and so on until an minus 1, and b equals to b0, b1, b2 until bn minus 1. We will view them as the polynomials a of x equals to a0 plus a1x plus a2x squared plus and so on plus an minus 1 x to the n minus 1, and b of x equals to b0 plus b1x plus b2 to the x squared and so on plus until plus bn minus 1 to the n minus 1. And we will seek to compute their product c of x equals to a of x times b of x in big O of n log n time. If c equals to c0, c1, c2, and so on to c2n minus 2 is a vector of coefficients of c, then we recall from our earlier discussion that c is exactly the convolution a start b, and so we can then read off the desired answer directly from the coefficients of c of x. Now, rather than multiplying a and b symbolically, we can treat them as functions of the variable x and multiply them as follows. 1. First, we choose two n variables, x1, x2, x3, and so on until x2n, and evaluate a of xj and b of xj for each of j equals to 1, 2, 3 until 2n. 2. We can now compute c of xj for each j very easily. C of xj is simply the product of the two numbers a of xj and b of xj. 3. Finally, we have to recover c from its values on x1, x2, and so on until x2n. Here, we take advantage of a fundamental fact about polynomials. Any polynomials of degree d can be reconstructed from its values on any set of d plus 1 or more points. This is known as polynomial interpolation, and we will discuss the mechanics of performing interpolation in more detail later. For the moment, we simply observe that since a and b each have degree at most n minus 1, their product c has degree at most 2n minus 2. And so it can be reconstructed from the values c of x1, c of x2, and so on until c of x2n that we computed in step 2. This approach to multiplying polynomials has some promising aspects and some problematic ones. First, the good news. Step 2 requires only big O of n arithmetic operations, since it simply involves the multiplication of big O of n numbers. But the situation doesn't look as powerful as hoped for with steps 1 and 3. In particular, evaluating the polynomials a and b on a single value takes omega of n operations, and our plan calls for performing 2n such evaluations. This seems to bring us back to quadratic time right away. The key idea that will make this all work is to find a set of 2n values, x1, x2, x3, and so on until x2n, that are intimately related in some way, such that the work in evaluating a and b on all of them can be shared across different evaluations. A set for which this will turn out to work very well is the complex roots of unity. The complex roots of unity At this point, we are going to need to recall a few facts about complex numbers and their role as solutions to polynomial equations. Recall that complex numbers can be viewed as lying in the complex plane, with the axes representing their real and imaginary parts. We can write a complex number using polar coordinates with respect to this plane as r times e to the theta I, where e to the pi I equals to -1 and e to the 2 pi I is equals to 1. Now, for a positive integer k, the polynomial equation x to the k equals to 1 has k distinct complex roots, and it is easy to identify them. Each of the complex numbers, omega of jk is equals to e to the 2 pi ji divided by k, for j equals to 0, 1, 2, and so on until k minus 1, satisfies the equation, since e to the 2 pi ji divided by k, then to the kth power is equals to e to the 2 pi ji, which is equals to e to the 2 pi I, then to the power j. And since we know that e to the 2 pi I is equals to 1, then this becomes 1 to the power j, which is equals to 1. And each of these numbers is distinct, so these are all the roots. We refer to these numbers as the kth roots of unity. We can picture these roots as a set of k equally spaced points lying on the unit circle in the complex plane, as shown in figure 5.9 for the case k equals to 8. For our numbers x1, x2, x3, and so on until x2n, on which to evaluate a and b, we will choose the 2nth roots of unity. It's worth mentioning, although it's not necessarily for understanding the algorithm, that the use of the complex roots of unity is the basis for the name fast Fourier transform. The representation of a degree d polynomial p by its value on the d plus 1th roots of unity is sometimes referred to as the discrete Fourier transform of p, and the heart of our procedure is a method for making this computation fast. A recursive procedure for polynomial evaluation. We wanted to decide an algorithm for evaluating a on each of the 2nth roots of unity recursively so as to take advantage of the familiar recurrences from 5.1, namely t of n is less than or equals to 2 times t of n divided by 2, then plus big O of n, where t of n in this case denotes the number of operations required to evaluate a polynomial of degree n-1 on all the 2nth roots of unity. For simplicity in describing this algorithm, we will assume that n is a power of 2. How does one break the evaluation of a polynomial into two equal-sized subproblems? A useful trick is to define two polynomials, a even of x and a odd of x, that consists of the even and the odd coefficients of a respectively. That is, a even of x is equals to a0 plus a2x plus a4 times x to the square, and so on, plus a n minus 2 times x to the n minus 2 divided by 2. And a odd of x is equals to a1 plus a3x plus a5x squared, and so on until we plus the last term, a n minus 1 times x to the x minus 2 divided by 2. Simple algebra shows us that a of x is equals to a even of x squared plus x times a odd of x squared. And so this gives us a way to compute a of x in a constant number of operations, given the evaluation of the two constituent polynomials that each have half the degree of a, Now suppose that we evaluate each of A even and A odd on the nth roots of unity. This is exactly a version of the problem we face with A and the two nth roots of unity, except that the input is half as large. The degree is n minus 2 divided by 2 rather than n minus 1, and we have n roots of unity rather than 2n. Thus, we can perform these evaluations in time t of n over 2 for each of the A even and A odd for a total time of 2 times t of n over 2. We are now very close to having a recursive algorithm that obeys 5.1 and gives us the running time we want. We just have to produce the evaluations of A on the two nth roots of unity using big O of n additional operations. But this is easy given the results from the recursive calls on A even and A odd. Consider one of these roots of unity, omega. J to n, which is equals to e to the 2 pi ji divided by 2n. The quantity omega j to n to the square is equals to e to the 2 pi times ji, then divided by 2a, then the whole thing to the power of 2, where we can cancel out the term 2, and it becomes 2 to the e to the 2 pi ji divided by n. And hence, omega j to n to the square is an nth root of unity. So when we go to compute a of omega j to n, which is equals to a even of omega j to n to the square plus omega j to n times a odd of omega j to n to the square, we discover that both the evaluations on the right hand side have been performed in the recursive step. And so we can determine a of omega j to n using a constant number of operations. Doing this for all 2n roots of unity is therefore big O of n additional operations after the two recursive calls, and so the bound t of n on the number of operations indeed satisfies t of n, which is less than or equals to 2 times t of n divided by 2 plus big O of n. We run the same procedure to evaluate the polynomial b on the two nth roots of unity as well, and this gives us the desired big O of n log n bound for step 1 of our algorithm online. Polynomial interpolation. We've now seen how to evaluate a and b on the set of all 2nth roots of unity using big O of n log n operations, and, as noted above, we can clearly compute the product c of omega jn, which is equals to a of omega j to n times b of omega j to n in big O of n more operations. Thus, to conclude the algorithm for multiplying a and b, we need to execute step 3 in our earlier outline using big O of n log n operations, reconstructing c from its values on the 2nth roots of unity. In describing this part of the algorithm, it's worth keeping track of the following top-level point. It turns out that the reconstruction of c can be achieved simply by defining an appropriate polynomial, the polynomial d below, and evaluating it at the 2nth roots of unity. This is exactly what we've just seen how to do using big O of n log n operations, so we do it again here, spending an additional big O of n log n operations and concluding the algorithms. consider a polynomial c of x equals to the summations of cs times x to the s, summing for all s starting from 0 to s equals to 2n minus 1, that we want to reconstruct it from its values c of omega s to n at the 2nth roots of unity. Define a new polynomial d of x equals to the summations of gs times x to the s, summing for all s starting from 0 to 2n minus 1, where ds is equals to c of omega s to n. We now consider the values of d of x at the 2nth roots of unity. At the 2nth roots of unity. D of omega j to n is equals to the summations of c of omega s to n times w times omega j to n to the s, summing for all s starting from 0 to 2n minus 1, where we can replace c of omega s to doubling summation. With doubling summation, we still keep the summation for the index s summations of s starting from 0 to 2n minus 1, and the inner summation, the summations of t starting from 0 to 2n minus 1 t of the term will take times omega s to n to the t cos t omega j t starting from 0 to 2n minus 1, which is equals to the summations of t starting from 0 to 2n minus 1. Omega we just replace the sequence of the omega s. We take the omega s of t out of the inner summation omega j to the s. Then we take out the constant ct, because right now the ct is still under the enclosures of the index t. So that right now becomes ct times some inner summation. And the inner summation is for index summing with index s starting from 0 to 2n minus 1 of the term ws to n to the t times omega s to n to the t times omega j to n to the s. By definition. Now recall that omega of s to n is equals to, by roots of unity, that will be equals to e to the 2 pi I, then divided by 2n, then to the s. Using this fact and extending the notation to omega s to n equals to e to the 2 pi I divided by 2n, then to the s. Even when s is greater than or equals to 2n, we get that d of omega j to n is equals to the summations of t starting from 0 to 2n minus 1 of ct times the summations of index starting from s equals to 0 to 2n minus 1 of the term e to the 2 pi I times st plus js, then divided by 2n, which is equals to the summations of t starting from 0 to 2n minus 1 of ct, then times the summations of omega t plus j to n to the s, with s starting from index 0 to s equals to 2n minus 1. To analyze the last line, we used the fact that for any 2nth root of unity omega not equals to 1, we have the summations omega to the s summing with x s starting from 0 to 2n minus 1 is equals to 0. This is simply because omega is by definition a root of x to the 2n, then minus 1 is equals to 0. Since x to the 2n, then minus 1 is equals to x minus 1, such a term, times the summations of x to the t summing for all t starting from 0 to 2n minus 1. And omega is not equals to 1. It follows that omega is also a root of the summations of x to the t summing with index t starting from 0 to 2n minus 1. Thus, the only term of the last line's outer sum that is not equal to 0 is for ct such that omega t plus j to n is equals to 1. And this happens if t plus j is a multiple of 2n, that is, if t is equals to 2n minus j. For this value, the summations of omega t plus j to n to the s, summing for all index s starting from 0 to 2n minus 1, is equals to the summations of 1 summing with index s equals to 0 to s equals to n minus 1, which is equals to 2n because we have 2n terms. So we get that d of omega j to n is equals to 2n times c 2n minus j. Evaluating the polynomial d of x at the 2nth roots of unity thus gives us the coefficients of the polynomial c of x in reverse order multiplied by 2n each. We sum this up as follows. For any polynomial c of x equals to the summations of cs times x to the s summing with s starting from 0 to 2n minus 1, and the corresponding polynomial d of x equals to the summations of c of omega s to n times x to the s summing with s starting from 0 to 2n minus 1, we have that cs equals to 1 over 2n times d of omega 2n minus s to n. We can do all the evaluations of the values d of omega 2n minus s to n in big O of n log n operations using the divide and conquer approach developed for step 1. And this wraps everything up. We reconstructed the polynomial c from its values on the 2nth roots of unity, and then the coefficients of c are the coordinates in the convolution vector c equals to a star b that we were originally seeking. In summary, we have shown the following. Using the fast Fourier transform to determine the product polynomial c of x, we can compute the convolution of the original vectors a and b in big O of n log n time.